So in today's lecture, we are going to step it up and start looking at a little bit more complex of a cross-section from the simple circular shafts that we looked at previously. So in this section, we are going to look at what happens when we have a torque applied to a thin-walled shaft, and we're also going to look at what happens when we apply a torque to non-circular solid shafts as well. So the theory that we use to derive the equations is a bit more complex than what we used in circular shafts. In fact, we're going to rely on some energy theory equations, and we're going to rely on some elasticity theory equations for the non-circular shafts. Now, both the energy theory and the elasticity theory, we're not going to go into a whole lot of detail in this course. Those are more suitable for a higher level solid mechanics course, so you can take an advanced mechanics and materials class where you'll go into those a lot more in depth. What I really want you to take away from this lecture is I'm going to use the theory to derive the equations, but I want you to understand how to apply the equations. Me introducing the theory to you in this chapter sections or in these chapter sections is mostly just so that you understand that I'm not just inventing these equations. There is some actual theory that we're using in order to derive these equations. But once again, I will not ask you to derive these equations on a test. I'm more interested in your ability to then use these equations to solve problems on a test or your exam or your homework. So like I said, the theory is going to be a little bit more complex. I will try and explain it in the clearest way that I can, but once again, how we apply that theory is what's truly important for this, because this is just a basic solid mechanics class, mechanics and materials class. If you really want to dive into the in-deep kind of meat of this theory, you won't see that typically into like a graduate level solid mechanics course. Okay, so let's jump into it. The first thing that we're going to cover today is going to be thin-walled tubes. So let's go ahead and look at our example problem that we're going to try and build the theory to be able to solve at the end of this section. So here is our problem. We have a tube is made of bronze. It's a square tube, as you can see from the picture, and it is a hollow tube, so it has a thin wall section. And we'll go into this in a lot more detail when we solve it. What we're trying to do in this section is we're going to introduce the concept of shear flow, and we're going to use that shear flow concept to derive equations for both shear stress and for angle of twist when we apply a torque to a hollow shaft like as this, or such as this. And then once we have all those kind of equations derived, we're going to go ahead and we're going to look at this shaft, and we are going to solve for the shear stress at locations A and B, so at locations A and B here, and we are also going to solve for the angle of twist of the free end C. That's kind of what our goals are as we go through this section. So what we're going to start talking about here first is we're talking about torsion of thin-walled tubes. So far we've only analyzed circular shafts. We've looked at both kind of solid shafts and we've looked at hollow circular shafts, but we've looked at shafts where the polar moment of inertia is easy to calculate. So we were able to easily calculate the polar moment of inertia for both solid circles and hollow circles. So what we are going to do now is we are actually going to change gears, and we're going to look at completely different theory in order to analyze thin-walled tubes. So thin-walled tubes, we have some rules of thumb here. We have, if we're going to analyze a shaft as a thin-walled shaft or a tube as a thin-walled tube, we're saying that the thickness of the tube, the wall thickness should be less than 10% of the smallest overall dimension of the tube. So an easy way to think about it is, let's say I have a 2-inch diameter pipe. If I have a 2-inch diameter pipe, my wall thickness needs to be less than 0.2 inches. In fact, 0.2 inches is almost a quarter of an inch, and you're really kind of pushing it. I would say well less than 10% in order for these kind of assumptions to hold true. Okay, we have some examples of some thin-walled tubes shown on the right. I do want to say that we have some other requirements in order for this stuff to be correct. We can't have any slices or missing areas out of the tube. And the other big thing that we can't have is the tube can't have any large convex shapes in it. So while I have a picture of some thin-walled tubes here, I want you to notice like this shape here, where it has this change in concavity in this location, this tube would not be suitable for analyzing with this theory. So we are looking for things that are all kind of convex. Everything is outward. We don't have any chunks of the tube that then flip into the inside, towards the inside of the tube. So any reverse kind of concavity sections such as this are actually not are a lot more complicated to solve. So this would not be good to solve these kind of problems. Okay, so when we're dealing with thin-walled tubes, we have a couple of assumptions that we have to make. So I'm kind of covering up the pictures. Let me hide this. So we have a couple big assumptions that we have to make when we're dealing with thin-walled tubes. And the first assumption that we're making is that the shear stress is constant through the thickness of the tube. So here we have a kind of a differential element that we're trying to show here of the cross section of a tube. And I want you to notice that throughout this differential element that the thickness is not constant. So in case we're over here at location B, we have a thicker cross section than we have over here at location A. So our first assumption is that the shear stress is constant through the thickness. The shear stress here is also constant through the thickness. Now recall from circular shafts that this is not actually the case. The shear stress is actually larger the closer you get to the outer radius of the shaft. So this is an assumption because it makes it easier for us to analyze the problem. It's not 100% accurate. So it's very important for me to, I want you to recognize here that these assumptions that we're making when we're analyzing shear wall tubes, there is error associated with them. So while they are good approximations, they are not going to be 100% accurate, especially when we deal with tubes that are non-circular in cross-section, because anywhere that we have like sharp corners or changes in the surface, we are going to have stress concentrations that are not going to be accounted for by using this theory. So a big thing that I want to make sure that you understand is if you are ever designing something with a thin walled tube in mind and you're using less than a 50% safety margin, so we're talking a safety factor of less than 1.5, I don't know if I would use this particular theory. I'd probably lean more heavily into doing some finite element analysis or the finite element method to get a little bit more holistic view of what the stresses are actually doing in the shaft. But this is a really good first pass, and if we're going to have large safety factors, then it's probably acceptable for us to oversize or over-engineer a shaft if the cost of materials or the weight is not important in our design. Okay, so what we are going to do then is, since we have decided, or we are assuming, that the shear stress is constant through the thickness of the wall tube, the next thing that we're going to assume is we're going to assume that if we go around the perimeter of this thin-walled shaft, I'm trying to show here with my cursor, is we are going to say that every unit length, so if we have a differential slice of this tube this way, we're going to say that every differential length is going to support the same shear stress or shear force going all the way around the circumference of that tube. So if I have a circle and I look at some differential slice at the top, that differential slice is going to carry the same shear force as a differential slice at the bottom. And if we make those assumptions, we are going to define something that we call the shear flow. So the shear flow is then going to be defined to be, we're going to use the variable Q for it, but it's going to be the shear stress times the wall thickness at any given location. Okay, let me try and explain that a little bit more clear. So we're saying that at any location, at any particular location around the edge of this tube, we're saying that the shear flow, or we're assuming that shear flow is going to have a constant value, because we're saying that every portion, any differential slice around the circumference of that tube is going to carry the same force. So Q, the shear flow that we're defining as Q, is going to be constant around the circumference of our tube. Okay, now that means if Q is constant and we have a variable thickness T, the shear stress at different circumferential, however you would say that, at different locations around the circumference of the tube is not going to be constant. Okay, so anywhere that we have a different thickness, different wall thickness, we are going to have a different shear stress. So let me hide this camera again and we can look at this this slice that we have. So if I'm looking at here, we are saying that even though that shear stress is constant throughout the thickness at location A, and the shear stress is constant throughout the thickness at location B, the shear stress at A does not equal the shear stress at B. We're going to say that the shear stress at A times the thickness at A is going to be the shear flow at A, and the thickness at B times the shear stress at B is going to be equal to the shear flow at B. So we get the fact that our main assumption is that the shear flow is constant throughout the circumference of the shaft. So we're saying that the shear flow at A is equal to the shear flow at B. So as we can see, because the thickness at B is greater than the thickness at A, the shear stress at B must be less than the shear stress at A. Okay, so now that we have defined what shear flow is, let's take a look at a thin-walled shaft, and let's start doing some derivation in order to get our equation. So what I want to do first is I want to make sure that we understand what we are defining to be our coordinate system here. So we are saying that the x-axis runs parallel to the length of the shaft. And now we are to define a term S. ds is going to be an arc length. So if we draw a line around the circumference of the tube, we are going to say that ds is going to be in the arc length direction. So the arc length direction is going to have a value of the S axis is going to be tangent to our circumference at any point as we move around around the circumference of the shaft. So the big thing that we're talking about here, so let's now consider a slice. We're going to consider a slice of this shaft. So we have some thickness of our wall thickness that we defined, and then we have a dx. We're looking at a differential volume along the length of this shaft, and then we have our ds differential volume, which is going to be defined along the circumferential direction of our shaft. Okay, so we said that our shear stress is going to be constant throughout the thickness of the shaft. So we can say we have a constant shear stress. So we can say that this differential slice of this tube is going to create a differential force. There's going to be a differential force, which is going to be the shear stress times some differential area. And from our diagram, that differential area is going to be the thickness of the tube times this differential circumferential length, this differential arc length around the outside of the shaft. Okay, so that is going to be a differential force created by this shear stress inside of this hollow tube. So this differential force is going to create a moment around the centroid of the tube. So this tube is going to have its centroid. We are locating it, or we are defining it to be at location O here, the origin here. And we can say that that differential force, which we're showing right here, is going to then, the differential force due to this slice of the shaft is going to be in this direction as defined by the shear stress, and it's going to create a moment about the centroid of the tube. So we're going to create a moment about the centroid of the tube, and if we do that, if we integrate this value all the way around the circumference of the shaft, we're going to end up with the total externally applied torque to the shaft, and that must be the case. So what we're saying here is we're saying that if we apply an external moment to this shaft, then it's going to be split up along the length of this tube, or along the circumference of this tube, and the sum of the differential forces around the length, or around the circumference of this tube are going to sum up to be the externally applied torque that we have in this thin-walled shaft. So that's what this means right here. So this integral here with this closed circle S means that this is an integral about a closed linear path. So an integral about a closed linear path, and we're saying, okay, if I integrate all the way around the circumference of this tube, my lever arm distance is going to be r, my df is going to be my differential force, and that is going to be the moment that I am generating. And we said just a while ago that we figured out what df was. Df was our shear stress times our thickness times ds, and we defined shear stress times thickness to be shear flow. So if we integrate all the way around the circumference of the shaft, we get the radius times the shear flow is going to be equal to the torque. So once again, integrating around a closed linear path all the way around the circumference of the tube times the radius times the shear flow is going to give us our externally applied torque. So next we said one of our major assumptions when dealing with thin wall tubes is that the shear flow is constant around the circumference of this tube. So the shear flow is going to be constant. Since the shear flow is constant, we can pull it out front of the integral, and we're left with our externally applied torque is going to be equal to our shear flow plus this circumferential integral of the radius, the radius around the circumference of the tube. Now this integral, although it appears to be simple looking at it mathematically, is actually a very challenging integral to evaluate. So we have to kind of be clever with how we want to go ahead and evaluate this integral. So the way that we're going to recognize how we can evaluate this integral is we are going to look at what we call the mean area of the tube. So once again, we have this dotted line that we have shown here. This is the circumference of the tube that we're looking at. And it is important to notice that this is passing through the center of the wall thickness. So we are assuming that because it's a thin wall tube, we can treat the radius as almost a constant value at that angular location. So at any angular location, we are just going to say that the radius is a constant value, and that radius is going to be about the average of the radius between the inside wall and the outside wall. So that's important that we recognize that this distance, this radial distance r that we are traveling around the outside of the tube passes through the center of the wall thickness. Okay, so now that we're looking at this surface here, we're going to notice that for our differential arc length ds, we can create this blue triangular area here, and they're calling it the height of the triangle. I'm calling it r, which is the radius of the distance from the centroid to the mean distance between the thickness, so the mean distance between the inside thickness and the outside thickness. And we can recognize that if we define this to be some differential area in the blue triangle, it's going to have a value of the area of a triangle, which is 1/2 times the radius times this ds. So that's just the 1/2 base times height is going to be the area of this triangle, which we can then multiply both sides by 2 to move this 1/2 to the other side of the equation, and we get that rds is equal to 2 times this differential area here. And this is where the trick comes into play. Because we were able to define this RDS here, we can then plug RDS back into this integral that we have up here. So now what we're saying is that our externally applied torque is going to be equal to 2 times the shear flow times the integral around this circumference of the differential areas of the differential area DAM. So if we integrate this differential area around the entire perimeter of this thin wall tube, we get just what we call the mean area. So I'll hide my camera again. We get what we call the mean area, and this mean area is the area of our hollow shaft of the line drawn midway through the wall thickness all the way around. So now we can say we have a new equation. This is one of the most important equations in this chapter, as we can say that the shear flow is going to be equal to the externally applied torque divided by 2 times the mean area. And this is kind of the big takeaway that we have. We can use this equation right here and this equation right here, which is the definition of shear flow. We can then relate shear flow to wall thickness times the shear stress. So we end up, if we combine, which I didn't draw it here, but we can combine these equations, and this becomes the most important equation is going to be that we have our Q, our shear flow, is defined to be the shear stress times the wall thickness T is going to be equal to the externally applied torque over 2 times our mean area. Okay, this right here is going to be a big takeaway for how we solve for shear stress, in a thin walled tube. Okay, now just as we did with all of our other our circular tubes, we're not only going to be interested in the shear stress. So once again, I want to just remind you that there are kind of 2 main ways that we may have kind of design requirements when we're talking about shafts applied to externally applied torque. We're going to say that number 1, the shaft cannot fail. The shaft cannot fail. So if the shaft cannot fail, that means we're designing based off of stress. So we want to know what the maximum shear stress is so that we can design for failure. The second thing that may be important depending on our application is that we can have a maximum angle of twists, right? So if I have a shaft and I'm going to apply a torque on it, I may have a shaft that it won't fail under a given torque, but under that given torque, there's going to be a relative angle of twist through that shaft that's going to be so great that it's going to mess up the geometry of our system, right? So I may have to design my shaft that's holding an external torque. I may say, okay, it can only deflect 2 degrees. It can only deflect 5 degrees. How much it can deflect is going to be dependent on your problem, but those are the two main ways that we're going to have to design shafts, is we have to design them so that they don't fail and so that they don't twist an excessive angle of rotation when you apply the torque to them, because that excessive twist may cause your system to no longer act in the way that you designed it. So if we're interested in shear stress, which is kind of what we just talked about, we're also going to be interested in angle of twist, or the deflection angle of rotation along the length of the shaft. So let's go ahead and take a look about how we think we're going to derive that, and we're going to derive that using the strain energy theory. Okay, so as you learned in Physics 1, we have what we call work, which we can equate to energy. So recall that work is a force acting through a distance. So a force acting through a distance does work, and that work we can equate to energy using the work-energy theorem. And the same sort of thing applies to a torque. You probably remember from Physics 1, 2, that we can also equate energy to, if I have a torque and I apply it through an angle of rotation. So if I apply it through an angle of twist, then that also equates to work, which I can equate to energy. And that's what we're going to use here to derive this equation. So we can say I have the strain energy of a system is going to be the energy required to deform a body. It's going to deform a body. So the strain energy, if I look at, once again, we're looking at a differential slice of our tube that has some thickness dx. Let me hide my camera again. Has some thickness dx that is going to be along the length of the hollow shaft, and some circumferential length, some differential arc length ds that goes around the outside of the shaft. As I apply this externally applied torque, this differential element is going to deform. It's going to, this edge is going to move with respect to this back edge. And we defined in chapter 1, we have what we call a shear strain. And a shear strain is going to be the angle in radians from any surface or any line or surface that used to be parallel. As it gets deformed through an angle, we define that to be shear strain. So what we are going to say is we're going to say that our differential energy required to deform this differential element, is going to be some differential force acting over a distance. Now we already determined what that differential force was in the previous section. We said that differential force is just the shear flow times that differential length. And now we know what this distance that it's going to be deformed is going to be the shear strain times dx. Now for this, we're using this small angle approximation for sine of gamma, for sine of the shear strain. So we're saying that since this shear strain is going to be small, it would be dx sine of gamma, but because gamma is small, we can just say that it's approximately gamma times dx. So the small angle approximation is one of those very, very common assumptions that we use a lot in engineering proofs. Okay, so now we can say that the differential energy used to deform this differential element is going to be the shear flow times the differential arc length around the outside of the tube times the shear strain times some differential longitudinal distance of this differential element that we are looking at along the length of this tube. So we can say from Hooke's law, from chapter 1, that our shear strain is equal to our shear stress divided by our modulus of rigidity. Okay, so our shear strain is equal to our shear stress divided by our modulus of rigidity, which we can then plug that back into the previous equation for gamma right here. So when we plug that in, we get this new equation for our differential energy, where we have the shear flow times the shear stress divided by the modulus of rigidity times that ds dx lengths. Okay? Now we defined shear flow as being the shear stress times the thickness. So I can then plug in for my shear stress, I can plug in Q over T, and I end up with this form of the equation right here. So we have to integrate this twice, because this is a double differential here. We have a ds and a dx. So we can say, okay, if I integrate this, I have to integrate this not only from 0 to L, so if L is going to be the length of my shaft, let me go back to a regular pointer. So if we're going to go back to the length of my shaft, I'm integrating from 0 to L along the length of my shaft, because this is the x direction here. But we are also going to be integrating around the circumference of our hollow shaft, and we're integrating this ds over dt. The next thing that we want to make sure that everyone remembers is that we are saying that our shear flow, once again, is constant. It does not change with respect to s, and it's also not going to change with respect to L, so it gets pulled out in front of the integral. And our modulus of rigidity is the same. That is just a material property. It does not depend on location of the shaft. It is just a function of the material. So it gets pulled out in front of the integral as well. Okay? So this next step that we have here, where we jump down here, is if we have a constant cross-section along the length of our shaft. So our cross-section of our shaft does not change along its length. If it's just a constant 2-inch diameter hollow pipe, then there is no variation in the x direction. So if we integrate from 0 to L dx, there is no variation. That just becomes the length. And that comes out in front of the integral as well. So our integral simplifies into this shear flow squared times the length divided by the modulus of rigidity, plus this kind of closed linear integral around the circumference of the tube of ds divided by t. So we are going to come back to this term here in a second. Well, let's go ahead and try and move forward and see what we can do to equate the rest of this, because this is still in terms of energy. This is still in terms of U is energy, which is the energy required to rotate this shaft through an angle. But we are not interested in the energy required to rotate this shaft through an angle. We're actually interested in the angle itself. So recall, like we said earlier, that the energy required to twist a shaft through an angle phi is going to be the torque times that angle phi. That is going to be, instead of a force times a distance, we have a torque times an angle is also a way that we can calculate work. So now we want to simplify this problem, or simplify this equation, for phi. We're after phi here because we're interested in what is the angle of twist when we apply a torque to this hollow shaft. So we're going back to one of those first equations that we derived for shear flow, and we are going to go ahead and plug in for this q squared term. We're going to plug in our shear flow equation, which was equal to our externally applied torque divided by 2 times our mean area. So when I plug that into this equation here, and then I divide both sides by t, by our externally applied torque, I get this equation for our angle of twist. So this is all fine. We know what our externally applied torque is, or we can determine that from the problem. We should know what the length of our shaft is going to be. 4 is just a number. Modulus of rigidity is just going to be a function of the material being used, and our mean area we should be able to calculate from the cross-sectional area that's given for the problem. How do we evaluate this integral here, this integral around the circumference of our shaft of ds over t? Let's jump into that now. So the first case we're going to consider is going to be the simple case where that the wall thickness is constant throughout the entire shaft. So we're saying that the wall thickness does not change, and if that's the case, we can pull this t out in front of the integral, and if we just integrate around the circumference of ds, we just get what we call s, and s is going to be the circumference of the shaft. S is going to be the total circumference of the shaft. So that means that if wall thickness is constant, this is a pretty easy equation to evaluate. So we can say, okay, here example is going to be our equation for our angle of rotation for a hollow shaft, and let's practice with a simple hollow circular tube so we get an understanding of how we would calculate. The hardest terms to calculate here are going to be S and our mean area. So our circumferential length and our mean area. Okay, well, we said once again we're interested in the circumference passing through the center of the wall thickness. So then we can say that our circumference is going to be pi times this diameter. Well, our diameter is going to be our outer radius plus our inner radius divided by 2, so the average of the radiuses, and then we multiply that by 2 to get our diameter, and if we multiply that by pi, that is going to be the circumference of this dashed line. So we're looking for the length of this dashed line that passes through the center of our wall thickness. Okay, and our mean radius is going to be the exact same thing. The area of a circle is going to be pi r squared, but I'm not just going to use my inner radius and my outer radius. I have to use an average of those two values. I have to use average of those two values. So we can say that our mean area is going to be pi times our inner radius plus our outer radius divided by 2 squared, which I would then plug into this equation. And the arc length is going to be our pi times our diameter, or 2 pi r, so 2 pi times our average of our 2 radii. So that's how we would use these terms to calculate this s and this am term, because those are the hardest terms to calculate. So the next thing that we're going to say is if the cross section is composed of discrete sections, which means that we have different lengths. Different lengths of the tube. Or let's say that we have a square tube and the top is thick and the sides are thin and the bottom is thick. We are going to use that. We're going to split that up into discrete lengths. And we're going to split that up into discrete lengths. So we're going to have some length with a particular wall thickness, and if we have multiple different lengths and wall thicknesses, we have this summation. We have this summation of these terms, and that'll make a lot more sense when we work this example problem that we have coming up here. Okay, so let's jump into our case study solution for thin-walled shafts. So the problem reads, the tube is made of C86-100 bronze, which has a modulus of rigidity of 38 gigapascals and has a rectangular cross-section. And if it's subjected to the two moments, determine the average shear stress in the tube at locations A and B, determine the angle of twist at the end C. Okay, so let's go ahead and take a look at what the problem is saying. So we essentially have a rectangular hollow shaft which is fixed on one side. So we'll say that this is it is fixed back here at this back wall. Now it has two externally applied torques to it. So it has two externally applied torques. It has an externally applied torque here at its free end. So we have an externally applied torque here, and we're saying that that has a value of 60 Newton meters. And it has another externally applied torque of half a meter back on the shaft, but in the opposite direction. So we have another externally applied torque further back along the shaft, and it has a value of 25 Newton meters. So 25 Newton, let's draw that up here. 25 Newton meters. Okay, now the distance in between these two is half a meter. So where this torque is applied and this torque is applied, we have a distance of half a meter, and then the remaining distance of the shaft is going to be at 1.5 meters. Okay? Now it's asking for the shear stress at locations A and B. So let's go ahead and we'll start with the first part. We'll do the angle of twist later, but it's asking for the shear stress at locations, and we have A on top, or A on the side, and B on the top. So that's kind of what it's asking for. And I didn't draw it, but this is a thin-walled rectangular shaft. So it is a hollow tube with a rectangular shape. Hollow tube with a rectangular shape. So it looks something like that. Okay, so hopefully everyone's kind of clear with what the problem is asking. The first thing that we have to determine then is if we're after what the shear stress is at locations A and B, we're going to note that both A and B are inside this 1.5 meter length. They're inside this 1.5 meter length. So we need to determine what the internal torque is in this 1.5 meter length. And we can do that a couple different ways, but the easiest way to do that is I'm going to make a cut, just because this is kind of how we solve all these problems that we've solved, in statics and mechanics and materials. I'm going to make a cut at that location. So I'm going to cut that shaft in that interval, in that 1.5 meter length interval, and I should be able to solve for what my internal torque is at that location. So if I make a cut at that location, and then I consider the front half of the shaft, if I consider the front half of the shaft, so I'm not going to draw it as hollow, it doesn't really matter, but I'm going to say, okay, I'm looking at just the front half of the shaft. Okay, I still have my 60 Newton meter torque that's being applied in this direction. I still have my 25 Newton meter torque that's being applied in the opposite direction. Now, if I know that this shaft is in equilibrium, I have a torque being applied that's going to be counterclockwise when we're looking on end of 60, and then we have a torque that is clockwise, or the value that's pointing into the board of 25. So I know in order to be in equilibrium, I have to oppose the rest of this 60. So I have 25 already, but I have a 60 going counterclockwise, so I must have a clockwise torque of 35 Newton meters here at my cut in order to provide for equilibrium of this shaft. So now we've made a cut at locations A and B, and we've determined that our internal torque at that location is 35 Newton meters, and that's going to be the first piece of information that we need in order to solve this problem. So what do we do with that internal torque now that we know what the internal torque is at locations A and B? Well, we have to go back to shear flow. So once again, we'll just make a note here. We're going to say that our torque at our cut was 35 Newton meters. Okay, now I'm going to go ahead and erase this diagram right here. And let's go back to what we learned in this section where we defined a term that we called shear flow. So we said that shear flow was defined to be equal to the shear stress times the wall thickness of the shaft. The shear stress times the wall thickness of the shaft. And so anywhere that your shaft has a different wall thickness, you're going to have a constant shear flow, but you're going to have a different shear stress. So everywhere along this perimeter, this outside perimeter of this thin-walled tube, we are saying has a constant shear flow, but if our wall thickness is variable, then our shear stress must be variable, okay? And then we also derived the relationship that our shear flow is also equal to our internal torque at that location divided by 2 times our mean area. So those are the two big equations that we derived in this section for figuring out what the shear stress is in a thin-walled shaft. So now we need, in order to determine what's going on here, I know from the cross-sectional area diagram that was given, I can determine wall thickness at locations A and B. I need to determine what my mean area is. So let's go ahead and take a look at this cross-section and see if we can figure out what that is. Okay, so I tried to draw the cross-section as it was given to us in the problem, and I want you to notice that I drew it really exaggerated because I wanted to make sure it was very, very clear that the vertical sections of the rectangular tube are thicker. They're at 5 millimeters of thickness as opposed to the horizontal portion. So the top and the bottom are only 3 millimeter thick. So we do not have a constant thickness throughout this cross-section. I also want to know from looking at our diagram that A lies in the 5 millimeter thick section and B lies in the 3 millimeter thick section. Okay, so actually I'm going to go ahead and rewrite that A over here. So this is where A is. So there's going to be our wall thickness at our 2 different locations. Now what we're after here is we're after the mean area. So in order to determine the mean area, we have to go through and we have to draw a perimeter which goes along the center of our wall thickness. It goes along the center of our wall thickness at every location through this non-circular shaft or this hollow shaft. Okay, well, we can need to determine if this is the area inside this dash line that we're after, right? My overall outside diameter is 40. I have a wall thickness of 5 here and a wall thickness of 5 here. So this area, I'm moving in 2.5 here, and I'm moving in 2.5 here. So I move a total in of 5. So I end up moving 40 minus my wall thickness. So I can say that my mean area is going to have a width of 35 millimeters. In my mean area height, I can do the exact same way. It has a total height of 60, but because our wall thickness is 3 and 3, I move down 1.5 millimeters here, I move up 1.5 millimeters here, so I lose a total of 3 millimeters, which is the same as our wall thickness. So our height is going to be 57 millimeters. 57 millimeters. Okay, so that means if I go ahead and carry that multiplication out, my mean area is going to be 1995, so 1995 millimeters squared. And whenever we're working problems, it's always best to get back to our base units. So I want to drop this millimeter, so I have to get rid of millimeters, so times 1 meter over 1,000 millimeters. But we are millimeters squared, so I have to square this conversion factor, and I get that my mean area is in fact going to be 0.001995 meters squared. So now that we know what our mean area is, we can go back to our shear flow. We can go back to our shear flow equations, and we can start solving for our shear stress. Okay? So we can say, first of all, we're going to use this first equation, or I should say this second value for shear flow to solve for the value of shear flow. Once we know what the constant shear flow is, we can then divide it by the wall thickness to find our shear stress. So this was our big overall equation, and we're going to show you kind of how you use this in 2 steps to get to your shear stress. So I'm going to go ahead and make a note of this over here. Our mean area is equal to 0.001995 meters squared. Okay, so let's go ahead and erase this and get a little bit more room on the board. Okay, so let's use our second expression for shear flow. We are going to say that our shear flow is equal to our internal torque divided by 2 times our mean area. We already found that our internal torque at the cut where A and B were located was 35 Newton meters. So we have 35 Newton meters over 2, and we just found that our mean area was 0.001995. So we go 0.00995 meters squared. And you just plug that all in our calculator, and we get that our shear flow then is going to be 8771.9 newtons per meter. Remember that shear flow has units of force per unit length. We are saying that for every unit length around the circumference of this hollow shaft or this thin-walled shaft, it is exerting a force in order to give us this total torque. So we're saying a force per length, we can sum that force per that length around the circumference, and then I'll give us a torque about our centroid of our hollow shaft. Okay, well now that we know what our shear flow is, we can then use our first equation, our definition of what shear flow means, in order to determine what our shear stress is at A and B. So we can then say that our shear stress at A is going to be equal to our constant shear flow divided by our thickness at A. So we can say this is going to be equal to 8771.9 Newton meters. We are dividing this by our thickness at A. So our thickness at A was 5 millimeters, which we can then convert to meters is what we need to do. So we convert that to 0.005 meters, and we can do this in our calculator, and we figure out that our shear stress at A is 1.7544. So our shear stress at A is 1.7544 megapascals. And that is going to be one of the answers that the problem asked for. One of the answers that the problem asked for. Okay, I'm going to go ahead and erase this work above. And we do the exact same thing for our shear stress at B. We can say that our shear stress at B is equal to our shear flow divided by the thickness at B, which is still going to be the same. It's constant everywhere. Shear flow is constant throughout the entire circumference of our hollow shaft. So 8771.9 newtons per meter divided by our thickness at B is only 3 millimeters. Our thickness at B is only 3 millimeters, so it's going to be 0.003 meters. I go ahead and I do that calculation in my calculator, and I get that my shear stress at B is 2.9240 megapascals. So I went ahead and just divided, when I did this calculation, I went ahead and divided by 1,000,000 to get it into megapascals. Okay, that's all I did was convert it from pascals to megapascals by dividing by 1,000,000. So let's step back and let's take a look at what this is saying. And it should make fairly intuitive sense. We discovered through this calculation that our shear stress at location B is much higher. I should say much higher, but it's a fair bit higher than our shear stress at location A. And like I said, that's what we would expect to happen. We would expect B, because it has a thinner wall here at B, to have to carry a higher stress. Well, what does that relate to this shaft? Well, that higher stress is going to be our best indication of failure. If we were to apply a torque to the shaft to the point where it fails, we would expect it to fail on this top or this bottom surface first. On the thinner sections of that wall, we would expect that top surface or that bottom surface to fail first before these side surfaces are, because there's just more meat here, right? There's more thickness here, so this hollow shaft or this thin wall tube is stronger along these vertical runs than it is along these horizontal runs. So this is a good indication, or this agrees with what we would expect to be happening. What it makes intuitive sense to us is that the top and the bottom should carry a higher stress than the sides. The top and the bottom should carry a higher stress than the sides. Okay, for the second part of the problem here, we are asked to find the rotation of the free end at point C from the diagram. So we need to split this up into two sections in order to figure out exactly what's going on. So what we got going on here is we're going to have we already solved for our cut back at A and B, that 35 Newton meter internal torque. That is also the reaction torque at the wall, which makes sense if I'm going to look at this entire shaft in equilibrium. If I have 60 Newton meters acting on the free end, I have 25 Newton meters acting at that location D, then at the wall, in order for it to be at equilibrium, our support reaction at the wall must also be that 35 Newton meters, because 35 clockwise plus 25 clockwise minus 60 counterclockwise is going to sum to 0. So we're using our static equilibrium equations. We know that the reaction torque at the wall has to be 35 Newton meters. Okay, if that's going to be the case, if I come out to here, this point D, where the 25 Newton meter torque is applied at location kind of D right here, right? If I made a cut right at D, I could say right on the other side of that 25 Newton meters, I'm going to recognize that I'm going to have that constant 35 Newton meter internal torque all the way through the length of this shaft from the wall to point D, And then once again, I'm going to have an additional torque inside from D to the free end at point C. So if we call the free end right here at point C, we have this half-meter distance is going to, if I make another cut right on the other side of D, it carries a 60 Newton-meter internal torque for equilibrium. So we need to be getting good at kind of analyzing what the torque is along different lengths of the shaft. Because they are just point torques, they're just torques applied at a specific location at the wall, at C, and at D, then when the internal torques in between those point torques are all the same. So the internal torque is constant all the way to point D, and then it jumps, so we have a shift, and then it's constant all the way to point C. Yeah, so we have 35, and then we have 60. 35, and then we have 60. So, that being the case, we need to go ahead and take a look at what our equation was for rotation of a thin-walled shaft due to applied torque. So we actually have to split this up into two problems. So our equation that we're going to use is we're going to use that our displacement angle is then going to be at location D. So we are going to say that we have a 35 Newton-meter internal torque all the way to D. That 35 Newton-meter internal torque is going to cause that free end to rotate at some amount, right? It's going to cause that free end to rotate at some amount. I broke it out and I drew pictures in your notes. So let's just go ahead and do that because it may make it a little bit easier for you to understand what I'm talking about. So once again, we have a shaft and I'm making a cut at point D. Okay, at the wall, we said our reaction torque was 35 Newton meters. And if I made my cut at point D for equilibrium, my torque applied to this free end, my internal torque applied to this free end is going to also be 35 Newton meters, just in the opposite direction. It's going to be a counterclockwise 35 Newton meters. Well, this just becomes a one shaft with just a torque applied to the end, and this is what we derived our equation for rotation at point D. So once again, I made our cut here at point D. So I'm going to say that my rotation of the shaft at point D, so phi sub D is then going to be equal to our torque between D and E, and once again this was location E at the wall, so our torque between D and E times the length between D and E divided by 4 modulus of rigidity times our mean area squared times the sum of our arc length over our thickness. This was our equation for rotation of a thin-walled shaft. Okay, so now we need to start just plugging in, our knowns for this equation. So we know that the torque between D and E, so we could say our free end rotation of D is going to be our torque, which is 35 Newton meters. We have the length from D to E was given as 1.5 meters. We have 4. The modulus of rigidity was given as 38 gigapascals, so 38 times 10 to the 9 pascals. And our mean area, we already found in the first part of the problem, our mean area was 0.001995 meters squared, and they want us to square that value. All right, that's everything in our leading coefficients. Now we have to multiply all this by this summation here. We have to multiply all this by this summation. So we need to say, okay, what are these terms? What are these terms? And I already erased our diagram of our cross sections. Let me just draw it up again real quick. Okay, now I want you to recall what we did for our mean cross section, where we drew our line through the center of the thickness of the thin-walled shaft all the way through the circumference. Okay, all the way through the circumference. So now we are going to use this length of our mean area. So this mean length, remember, was 57 millimeters tall, because we had that 60 minus that 3. And then we had this one was, I already forgot what it was, 35. Yeah, this one was 35. because we have the 40 minus the wall thickness of 5. So we have so we're going to have a multiplies here, and I'm going to go ahead and make this summation. So it's a rectangle, so I have two sides, which are 57 millimeters long, divided by a thickness of 5 millimeters. And then I have two horizontal sections, the top and the bottom, which are 35 millimeters long, divided by a wall thickness of 3 millimeters. Now, I don't want you to freak out here by not converting those millimeters to meters, because I'm dividing millimeters by millimeters, and I'm dividing millimeters by millimeters. So I didn't write that out explicitly, but we can go ahead and do that just to be a little bit more rigorous. Okay, so what I have here is I'm only really interested in the ratio of the length to the thickness. I'm only interested in the ratio of the length to the thickness because I have a millimeter on the top and a millimeter on the bottom. My units here actually cancel out. So this entire term in our summation is unitless. So I don't have to convert that fraction, that ratio term, from millimeters to meters, because then the units all cancel out because that's a unitless term. Okay, well, once I get to this point, I just plug all this into my calculator. It's just a bunch of numbers at this point. I just plug it all into my calculator, and I get that my rotation of point D is in fact going to be 0.004035. 0.004035, and this is going to have units of radians. This is going to be in radians. If you want to convert it to degrees, you can do that. This is going to be in units of radians. Now, looking back at my cut diagram here, we can say, okay, if this back wall is fixed at point E, then at D, my rotation is going to be counterclockwise. My rotation is going to be counterclockwise of point D. Okay, so I just went ahead and made a note of that up here, and this is going to be some common nomenclature that you might see, or a way of writing this out. I'm just going to write that the phi, the rotation angle of point D with respect to the fixed point E, we already found to be 0.004035 radians in the counterclockwise direction. Okay, now the problem was asking for the rotation of the free point at C. So just like we had relative twist between point D and point E, we're also going to have a relative twist between point C and point D. So once again, I need to make a cut at point D, but I'm going to look at the other side of that cut, the free end cut, and we're going to analyze that separately here. So once again, I have a much shorter length. Now, instead of it being 1.5 meters, it's only half a meter. And on my free end at location, so we're going to call this is C and this is D. On our free end at location C, we have 60 Newton meters applied. Well, for equilibrium, if I know that the whole shaft is in equilibrium, then this individual component of the shaft must also be in equilibrium. So that must mean that my internal moment on this other side is also going to be 60 Newton meters in the opposite direction. So now we have a much shorter length of shaft. Before we were analyzing a 1.5 meter length of shaft. Now we're only analyzing a 0.5 meter length of shaft, but we still have it such that it's just in a applied torque, right? Just an applied torque. But now we're going to figure out what the rotation of the free end C is with respect to point D. So instead of finding D with respect to E, which is what we already found, we're going to find C with respect to D. And then the total rotation of C with respect to E will be the summation of those two things together. So we use the exact same equation that we used before. We say that the free angle, or the rotation of point C with respect to D, is still going to be the internal torque of CD plus the length CD divided by 4, the modulus of rigidity, our mean area squared, and I'm out of room, so times the summation of SI over TI. I know that looks confusing, but I had to just drop it down so I don't go off the edge of y'all's screen here. So let's go ahead and start plugging everything that we know about this particular term for this equation. So our rotation angle of C with respect to D is going to be our internal torque is going to be 60 Newton meters. The length was 0.5 meters. We have 4. Our modulus of rigidity was 38 times 10 to the 9 pascals. We had 0.001995 meters squared times, once again, we have the same summation. The cross section hasn't changed along the length of the shaft, so we use the exact same summation that we used before. So we had 2 times 57 over 5 plus 2 times 35 over 3. So that's going to be the exact same summation. Those are all just numbers. We are now able to plug them into our calculator, and we can find that the rotation of C with respect to D is going to be 0.0022878 radians. And once again, looking at our diagram of our cut, C is going to rotate in the counterclockwise direction with respect to D. So that's also going to be counterclockwise. This means that our total rotation of free end C with respect to the fixed end E, I could say our total rotation of the free end C with respect to the fixed end E is going to be equal to our rotation of D with respect to E plus rotation of C with respect to D, which we already found, and they are both in the counterclockwise direction. They are both in the counterclockwise direction, so they just add directly. So this is 0.00400035 radians plus 0.0022878 radians. We add those together, we just plug them into our calculator, and we get 0.006262913 radians, which if I wanted to convert to degrees, I would multiply by 180 degrees over pi radians, and I would see that my free end rotation is going to be 0.3605 degrees. 0.3605 degrees. Well, okay, I hope that kind of makes sense how you work through these kind of problems. I'm only going to work one of these thin wall tubing problems because they get pretty long pretty quick. In fact, we've been working on just this one example problem for well over half an hour now. So this is kind of what we've solved. We were able to look at this diagram. We were able to figure out what the shear stress was in this length, this 1.5 meter length between point D and the wall, but we were also able to find the rotation of the free end C by using all the equations that we derived earlier in the chapter section. Well, okay, let's go ahead and jump into the next section in which we are looking at more general non-circular bars. So the first problem that we're going to work through, here's the example problem that we're trying to figure out how to solve, is we have ourselves a square shaft, but this time it's not a thin-walled shaft, it is a solid shaft. So we cannot use our thin-walled equations. We have to determine some equations for a solid shaft. Now, this section, I cover the material quite a bit differently than is covered in the ebook. The ebook just kind of says that non-circular shafts are incredibly complicated and they need to be solved numerically. While that is the case for a lot of general shafts, there are some shafts in which we do have closed form solutions. Now, how we would derive those closed form solutions are a little bit more complex than needs to be covered in this course. So I will kind of introduce the basic concepts of the theory that you would use to solve these non-circular sections, but then I just give you a whole bunch of different solutions that have already been solved by other people. So let's go ahead and jump into that. So when we talk about non-circular bars and shafts, things don't happen the exact same way that they happen with circular shafts. So for instance here, let's take a look at this square cross-section shaft, and we are applying a torque to it. We're applying a torque to it, and I'm going to go ahead and cover this up. So let's take a look at kind of what happens. And this is why non-circular shafts are so much more complex. They're so much more complex because when you apply that torque to that shaft, in a portion, a cross-sectional portion. So if I'm looking at just this line right here, if I was to make a cut along that line right here, whereas for a circular shaft, that cross-section would stay flat. For a square shaft or a non-circular shaft, that surface does not stay flat. In fact, it warps, and it warps in pretty complex and convoluted ways. And this makes solving these problems very, very hard, which is why the ebook kind of says it's easier just to solve them numerically. But let's kind of talk about how we would solve them if we did want to solve them. And we solve them using what we call elasticity theory. So elasticity theory, a lot of schools will offer a graduate level course only in elasticity theory, or a graduate level course in advanced mechanics and materials, which may cover some of this, this information. So I'm going to just be pretty quick with this, and you don't have to, don't feel like you have to understand this every equation line by line. I'm just trying to prove to you that that these equations for non-circular cross sections, where they come from, and they come from general elasticity theory. So if we have a 3D stress state as we've shown before. So we've kind of looked at stress states already, but here's a general 3D stress state. It's a volumetric element of dx by dy by dz, and it has 3 normal stresses and 3 shear stresses acting on it. Okay, so we can say that if we are looking for, if we know that this differential element is part of a rigid body which is in equilibrium, if the rigid body is in equilibrium, then this element is also in equilibrium. So we can apply our equations of equilibrium to this stress state. And the one that we're going to choose to apply is our sum of our forces in the x direction. So what we have acting in the x direction is we have a normal stress acting in the x direction, acting over an area of dz by dy. We have a shear stress acting, the shear stress xz acting in a dx by dy, and then we have a shear stress xy acting in a dz by dx. So we can sum those stresses times those areas together. That's our summation of our forces in the x direction are equal to 0. And then we can divide everything by the volume of the differential element, so dx times dy by dz, and we get this equation right here. We get this equation right here. So we can do the exact same thing in all 3 directions. If we do the exact same thing in all 3 directions, we get these 3 equations right here, and these 3 equations are kind of the foundation of elasticity theory. So these are the elasticity theory differential equations, and these are, when you move on to higher and higher level engineering, you get to these more and more complex differential equations. So this is kind of the solids equivalent of the Navier-Stokes equations for fluid mechanics, which you will cover in a fluid mechanics course. But what we're getting at here is that all of these terms are our normal stress in the x, our shear stress xy, and our shear stress xz, and our normal stress y, normal stress z, and our shear stress yz. They can all vary in all 3 dimensions. They can vary in the x, the y, and the z. So these are all partial derivative equations, because I'm taking the derivative of some function of x, y, z, but I'm taking that derivative only with respect to x. And I have some function of x, y, z, and I'm taking that derivative with only respect to y. And what that means is that these equations are very, very complex to solve. They're very, very complex to solve. So what we want to do is we want to simplify these fairly complex equations, which are our general elasticity theory equations, and let's look at them for the case in which we have a shaft in pure torsion. So if we have a shaft in pure torsion, we can say that our normal stress in all of our directions is going to be 0, because we have no externally applied forces. We only have an externally applied torque. And then we can also say that our shear stress in the YZ plane, so our shear stress about the YZ plane is 0, because our torque is about the x-axis. So since we have no torque about the y and the z-axis, so because we have no torque about the y-axis as I've drawn it on the board and about the z-axis as I've drawn it on the board. We only have a torque about the x-axis. I draw the x-axis as I drew it on the board. We don't have any shear stress in the xy directions. So if we do that and we go back to our previous three equations, we take those terms that we said were going to be 0, and these three equations then simplify. They then simplify to these three equations by plugging in everything that we have to be 0. So the last two equations indicate that we don't have any shear stress that varies along the x direction. So we said that our shear stress xy with the derivative with respect to x is going to be 0, and our shear stress xz, the derivative with respect to x, is going to be 0. So that means that our shear stress doesn't have any variation. There is no variation in the x direction, which makes sense. As long as our cross section of our shaft is constant in the x direction, then our shear stress should not vary along that x direction either. So what we're really interested in solving then here is we're interested in solving that first equation. We have our shear stress xy with the derivative with respect to y plus our shear stress xz, our derivative with respect to z. We sum those together and those are 0. So how do we solve that differential equation? So this differential equation is what we are trying to solve. So most of you haven't taken DiffyQ. DiffyQ is not required in order to take this class, so I'm going to try and be as brief with this as possible. But what we do is we define a scalar higher order shear stress equation. So I'm defining a higher order shear stress function, which I'm calling lambda, which is going to be a function of x, y, and z, but I'm going to define it so that it satisfies this equation. So I am just creating a solution to this problem, and I'm going to define it so that this equation must be true. And I can define it by saying that negative the derivative of lambda with respect to z is going to be equal to tau xy, and the derivative of lambda with respect to y is going to be equal to our shear stress xz. So if I then take the derivative of tau xy with respect to y, and I take the derivative of tau xz with respect to z, I end up with this derivative of lambda, this higher order function dy dz, plus this negative sign, plus that same derivative of lambda dy dz is going to be equal to 0. So this does in fact satisfy that differential equation. So these equations right here are how I define this higher order differential equation. So as it turns out, we can actually relate this higher order shear stress equation to our modulus of rigidity and the angle of twist phi. So the derivation of this relationship is going to be beyond the scope of this course, but I just want you to know that as it turns out, this is in fact true. Importantly, we can relate the externally applied torque back to our higher order shear stress equation, and this derivative is what we're going to do. So I'm not going to cover how we can prove these in this class, but if you look on Blackboard, I have a detailed proof of these two equations posted that I've taken from a higher level, a graduate level advanced mechanics and material class notes. I actually pulled that information, I have it posted, so you can read through those and look at them if you so desire. Let's take a look at an elliptical shaft, and I'm going to kind of show you how we figure this stuff out. But this is an elliptical shaft, and we're defining an elliptical shaft such that it has this distance is going to be A, this longer radius is going to be A, and this shorter radius is going to be B. And as it turns out, our higher order shear stress function is given in this form, So once we have this equation, once we have this, this higher order shear stress equation, we can plug it back into this integral. We can plug it into this integral, and we can use that in order to find a relationship between the torque and the angle of rotation phi. And then we can solve the equation. We just solve it for phi in order to get the angle of rotation as a function of this torque, right? As a function of this. And I have just given you here the equation for the maximum shear stress in a elliptical shaft is given by this equation right here. We can do those, we can take those exact same steps, and we can solve for phi and our maximum shear stress for a bunch of different shapes. I shouldn't say a bunch of different shapes, for a handful of different shapes. So there are closed form solutions to really, we have ellipses. Here I give you the closed form solutions for a square shaft, and I've given you the closed form solution for an equilateral triangular shaft. So these equations were all solved using elasticity theory. Now, it gets a little bit more complex, but I wanted to give y'all a bunch of other options of non-circular shapes, primarily so that you had some shapes to work with when you do your final design project. So for your final design project, I'm asking you to design a cross-sectional area, and you're supposed to solve for angle of twist. There's an angle of twist requirement and a shear stress requirement for designing that cross-section. So for non-square rectangular areas, something with a B and an H, it's a little bit more complex, but we have our angle of twist and our maximum shear stress depend on some constants K1 and K2, and K1 and K2 depend on the ratio of our base to our height. So our base is going to be the larger of the values, and it goes from anywhere from 1 to infinity. These constants will change depending on the ratio of B to H. So you can plug these in, and now we have some equations for angle of twist and maximum shear stress for a rectangular cross section. And then I want to go over what we call the torsion constant, and the torsion constant is something that is used regularly for solving specifically for angle of twist. So I want you to recall from circular shafts that we were able to find that the angle of twist was TL over JG, where J was the polar moment of inertia. Now, for non-circular cross sections, they wanted to find something, or engineers wanted to use something that was very similar to a circular shaft, so they defined something called the torsion constant K. The torsion constant K is the same as the polar moment of inertia, so it also has units of length to the power of 4, but we can say that our angle of twist for various cross-sectional shapes is going to be given by a very similar equation, which is going to be TL over KG instead of JG. Now, K can be found any number of ways. K can be found using elasticity theory. K can be found by performing a bunch of experiments, so it can be found empirically, and there are various different methods that are used for finding K, and I have just summarized those values of K that are given for various shapes. So I gave you the K for a hollow ellipse here. Once again, don't confuse this Q. This is no longer shear flow. This is some other constant Q, which is going to be the ratio of our of essentially the inside area, or the inside radius to the outside radius. So the ratio of the inside radius to the outside radius. For a thin-walled ellipse, where we assume that we have a uniform cross-section T, here's how we can calculate that K value. I give you K values for a square, so you could use, I gave you the closed form solution for a square already, but you can also use this value in order to solve it. This is the exact same thing as before. For a solid rectangle, this is whereas before we had different values K1 and K2, this is kind of a way that you can calculate K1 and K2 based off of A and B. So this is maybe a little bit simpler way to solve it, depending on which way you prefer. For a thin-walled rectangle, once again, we can take into account the different lengths having different thicknesses. So we have a thickness T on the vertical sections and a thickness T1 on the horizontal sections. Those all get applied when we solve for K. But the biggest reason why I wanted to show you this version is that we can use it to solve for the angle of rotation for an I-beam, the angle of rotation for an I-beam. Finally, I also wanted to include the torsional constant for common structural shapes that are used in steel construction. So here I have from the American Institute of Steel and Construction's Steel Construction Manual. I have the K values for C-channel that we show right here, for I-beams that we have right here, for unequal I-beams where you may have different flange widths on the top and the bottom, and the K values for angle iron, and also for T-channels as well. So for some commonly used construction or structural shapes in steel construction, I also wanted you to have the torsion constants for those. Okay, so let's jump into our case study solution for non-circular shafts. Okay, the problem reads, the 6061 T6 aluminum bar, which has a modulus of rigidity of 26 gigapascals, has a square cross-section of 25 millimeter by 25 millimeter, and it is 2 meters long. Determine the maximum shear stress in the bar and the rotation of one end relative to the other end. Okay, so in this case, the first thing that we notice is that we have a square bar. We have a square bar, and the problem asked for what is the maximum shear stress, and then it asked for the rotation of one end relative to the other. So we'll break this up into two problems, and we'll start with the maximum shear stress. So as soon as I see that it's a solid square bar, I go back to my notes previously that we just covered in the lecture. I go back and I pull my equation for a square bar. And we said that for a square bar, that the maximum shear stress was given as 4.81 times our maximum torque divided by A cubed, and that is the equation for our maximum shear stress. So we know everything that we need to know. We know what A is. It was given as 25 millimeters. I need to figure out what my maximum internal torque is, and that's easy to see from just looking at the problem. I can see that if I make a cut anywhere in this 1.5 meter length and I analyze it with respect to the left side, this entire section between the 20 Newton meter torque and the 60 Newton meter torque is going to have an internal torque of 20 Newton meters, right? If I make a cut here and I consider the left side for equilibrium, I have to have an internal torque of 20 Newton meters. The same thing I can do here. I can make a cut in between the 60 Newton meter torque and the 80 Newton meter torque, but this time I'm going to consider the right side. I'm going to consider the right side. So if I make my cut right here, and I then consider the right side of my cut, I know that my internal torque here, is going to be equal to 80 Newton meters in the opposite direction, right? It's going to be in the opposite direction. So if this is clockwise, this one is going to be counterclockwise with respect to looking at the shaft on in from this direction, right? So I can immediately see just from a quick making a cut and summing my torques to 0 for static equilibrium that my maximum internal torque is going to be 80 Newton meters. So that's pretty straightforward. So now I know everything that I need to know in order to solve this problem. So this is pretty easy to do. So this is going to be 4.81. Our maximum torque was going to be 80 Newton meters. Divided by A was given as 25 millimeters, or 0.025 meters cubed. Pretty straightforward. I know everything there is to know in that equation. I just plug it into my calculator, and I get that my maximum shear stress is going to be 24.627 megapascals. 24.627 megapascals. Okay, the second part of this problem asked us to determine the relative rotation of the ends with respect to each other. So if we call the ends in the diagram, they're calling it A, B, and C. I'm looking for the angle of twist in between A and C. Well, just like we did in the last problem, because I have this internally applied torque as well, I have to split this up into two problems. I'm going to have an angle of rotation between C and B, and I'm going to have another angle of rotation between A and B. So I can combine all that stuff together, and I can go ahead and write out my equation for a square shaft. So we have to go back in our notes. So we said that for a square shaft, our angle of twist is going to be it was 7.10 TL, or over A to the 4, TL over G was our angle of twist for a square shaft. Now once again, we are going to have two different lengths that we're considering, both of which are going to have different internal torque. So let's go ahead and make a cut over here just like we did before, and we can say, okay, if I'm going to make a cut in between A and B, we already found that it was going to be 80 Newton meters, going to be counterclockwise. I can make another cut over here between C and B, and I can say, okay, in this case, I have a torque that is going to be counterclockwise at C, so I must have a torque is equal to 20 Newton meters, and it is going to be in the clockwise direction. It is going to be in the clockwise direction in order to have equilibrium. As long as I'm looking down the shaft from A towards C, that is going to be my internal torque. Okay, so the angle of rotation can be confusing. So we can always go back to when we talked about internal torque diagrams, we can use internal torque diagrams in order to define what the magnitude, positive or negative, of our internal torques are, but I find it easier to go ahead and draw a picture. So I'm going to go ahead and draw a couple pictures here in which I make a cut at B. I make a cut at B and we consider CB, and then we consider BA. Okay, so let's go ahead and do that right now. So if I went ahead and I made a cut at B, right? Now we have our 20 Newton meter torque, 20 Newton meter torque applied to this end. And then we have, for equilibrium, we must have a 20 Newton meter torque going the opposite direction applied at point B. So let me go ahead and label my points. So I'm going to label my points C, and I'm going to label my points B. And what I want you to notice here is let's just pretend that C is fixed. Let's just say that C is fixed. If C is fixed, you see that B is going to then rotate clockwise. B is going to rotate clockwise. If I am looking from B towards C, B is going to rotate in this direction. Okay, I hope that makes sense. Let's do the exact same thing with our shorter cut from A to B. So now we have kind of the same cross-sectional shape. It's a little bit shorter this time, right? And now we say, okay, we have our applied 80 Newton meter torque, 80 Newton meter torque here at point A. Then for equilibrium at B, we must have 80 Newton torque going in the opposite direction at point B. So once again, if I am looking from A towards B, which is the same direction of from B towards C, my free end at A is going to rotate clockwise. It's going to rotate in the same direction. That's what I was trying to make sure everyone understands, so that when I apply the angle of rotation through the square shaft, B is going to rotate this way, and then A is going to rotate the same way more, if we consider C's being fixed. I hope that makes sense. So when we do is we're going to solve for the angle of rotation of B with respect to C, and then we're going to solve for the angle of rotation of A with respect to B, but they're both in the same direction. They're both in the same direction. They are both going to be clockwise if I'm looking from A towards C. If I'm looking from A towards C. Now, once again, here's our equation that we have for that. The 7.10 over A to the fourth and the modulus of rigidity do not change. The only things that change between our two angles of rotation are our internal torques and our lengths. So we can do the calculations together because we know they're going to be a summation of these rotation angles. We can just do the summation of the torque times the length, and we know that they're both going to be in the same direction. They're both going to be in the same direction. So I can rewrite that equation. I can rewrite that equation as theta of A with respect to C, so my rotation angle, I said theta phi of A with respect to C is still going to be 7.10 over A was given as 0.025 meters squared, all that to the power of 4. We are going to have a 1 over 38. Oh, 38 was the last problem. This one is 26 gigapascals. And now I have a summation of, it's going to be the torque between B and C times the length between B and C plus the torque between A and B times the length between A and B. So I probably should have written that kind of up here in this form of the equation, but now I kind of know everything that there is to know about this problem. So my torque between B and C, we found to be 20. Now I'm just going to be, for sign convention, if you actually go through and do the sign convention for internal torques, this ends up being a negative 20 Newton meters. So it's a negative 20 Newton meters times my length here was 1.5 meters, plus I have a negative 80 Newton meters because they go the same way. I'm going to run off the side of the screen. Negative 80 Newton meters times the length of half a meter, So now I know everything that there is to know in this equation. I just plug all this into my calculator, and I get that the angle rotation of A with respect to C is going to be a negative 0.048935 radians, which I can then multiply by 180 and divide by pi. It's going to be, to convert it to degrees, is a negative 2.804 degrees. Negative 2.804 degrees. Okay, let's work another problem for non-circular shafts to try and kind of illustrate how we look at triangular shafts. The problem reads, the 6061 T6 aluminum triangular shaft has an allowable shear stress of 8 KSI. The allowable twist angle is 3 degrees. Determine the maximum torque that can be applied. How much torque can be applied to a shaft of a circular cross-section made of the same amount of material? Okay, let's kind of get a picture of what we got going on here. It's not great, but we have a triangular cross-section. They gave us that it was 4 feet long and one side of the shaft is fixed. And then they give us that a torque is applied to the free end. They also said that it's an equilateral triangular shaft where all 3 sides of the triangle are 1.5 inches long. So let's go ahead and jump into this problem. This problem gave us 2 criteria that we had to meet in order to pass design. So it can have a maximum shear stress of 8 KSI, and it can have a maximum allowable angle of twist of 3 degrees. So what we're going to do is we're going to solve for the maximum torque that we can apply that will create both of those scenarios. So we'll solve for the torque that'll generate that 8 KSI of shear stress, and then we're going to solve for the torque that'll create 3 degrees of twist, and the lower of those 2 torques will be the maximum allowable torque that we can apply to this shaft. But, okay, so we see it's an equilateral triangle, so we jump into our class notes and we go pull our equations for an equilateral triangle, and we can start with our maximum shear stress, and we said that our maximum shear stress is going to be equal to 20 times our maximum torque over A cubed, Well, this one's pretty straightforward. They gave us a bunch of this stuff, and we can see from our diagram, if I make a cut anywhere on the interior of this shaft, that it's always going to have the same internal torque. It's always going to have the same internal torque equal to T, which is our applied torque. Okay, so that's going to be the case. We can say that our maximum allowable shear stress the problem gave was 8 KSI. So we have 8,000 PSI is our maximum allowable shear stress. And then we have 20 times our maximum torque divided by A was given as 1.5 inches cubed. 1.5 inches cubed. Okay, this is a pretty straightforward algebraic problem to solve. I just multiply 8,000 times 1.5 cubed, I divide by 20, and I get that my maximum torque, my allowable torque, we can call it allowable. Our allowable torque is going to then be 1350 inch-pounds. 1350 inch-pounds. Okay, our second option that we can set, our second criteria that we had to meet was that our maximum allowable angle of twist was 3 degrees. So we go and we look up in our table for a triangular shaft the angle of twist, and we had that our phi is equal to 46 over a to the fourth times t max L over G. Was our equation for a triangular shaft, okay? This was given to be 3 degrees, but remember that all of these equations are going to give our results in radians. So we're going to say that we need to have a 3 degrees is our maximum allowable angle of twist times pi radians over 180 degrees. We need to convert that on this left side of the equation. And that's going to be equal to 46 over 1.5 to the 4, our T max, which is what we're after again. Our length of the shaft in this case is going to be 4 feet times 12 inches per foot, all divided by the modulus of rigidity, which was given in the problem to be 3.7 times 10 to the 6 psi. So it did not give it in the problem. So I went and I looked up this modulus of rigidity from a material properties table. They gave us that it was 6061 T6 aluminum. I went and looked it up in a materials table, and the modulus of rigidity for 6061 aluminum is 3.7 MSI, or 3.7 times 10 to the 6 PSI. So now we have everything in this equation that we need except for our maximum torque T. So this just becomes a simple algebra problem. These are all just numbers that I just multiply 3 times pi divided by 180 times 3.7 times 10 to the 6 times 1.5 to the 4 divided by 46 divided by 4 divided by 12. And I can solve for my maximum allowable torque. And I get that my maximum allowable torque for 3 degrees of rotation is in fact 444.19 inch-pounds. So we see that from our first criteria, in which we could not exceed 8,000 psi in shear stress, we were allowed to put 1350, so 1,350 inch-pounds, whereas for our maximum rotation of only 3 degrees, we're limited to 444 inch-pounds. So this would be the answer to the problem. We would reach our 3 degrees of rotation well before we reach our 8,000 maximum shear stress criteria. So in this case, our maximum allowable torque that we can apply to the free end of the shaft is going to be 444 inch-pounds. Now, the second part of the problem asked us to then compare this to a circular shaft that uses the same amount of material. So I can say that if I want a circular shaft that uses the same amount of material as this triangular shaft, it's going to have the same cross-sectional area. It's going to have the same cross-sectional area. So that means I'm going to have a 4-foot-long circular shaft that once again is fixed down on this end, but this area has to be equal to this area. The area of the circle has to be equal to the area of the triangle in order to use the same amount of material, because the volume of the shaft is going to be our area, our cross-sectional area times our length. The volume of the shaft is going to be the cross-sectional area times the length. So the area of this triangle, if I said, okay, it's a 1.5, I can go ahead and draw it a little bit bigger. Let's draw it a little bit. If I have a 60-degree triangle, the area of 1/2 of this triangle is going to be 1/2 times base times height. So it's going to be 1/2 times, this is going to be 0.75. 1/2 times 0.75, and then this length right here is going to be 1.5 sine of 60. 1.5 sine of 60. I guess I don't have to split it up into 2 right triangles. I can just say that my my area of my triangle is still going to be just 1/2 base times height. So this is going to be 1.5. So I end up getting that my area of my triangle is going to be 1/2 times 1.5 times 1.5 sine of 60 degrees. Okay, and I said that my area of my triangle has to be equal to my area of my circle. So my area of my circle is going to be pi r squared, and that's going to be equal to that same area of my triangle, which is going to be 1.5 times 1.5 times 1.5 sine of 60 degrees. Okay, now I have an equation in which I have pi r squared is equal to 1/2 times 1.5 times 1.5 times sine 60. I know everything in this equation but r. I can algebraically solve for r, and I get that the radius of my circle is going to have to be 0.55689 inches. 689 inches. So now we know what the radius of our circular shaft that's going to use the same amount of material as our triangular shaft. Let's go ahead and make a note of that down here. We get that r is equal to 0.55689 inches. We'll erase this to make some room. Now from here, we just go ahead and solve the problem the exact same way that we just did for our triangular shaft, but now we're going to do it with a circular shaft. So we're going all the way back to the beginning of chapter 2 here, and we're going to solve it with ways that we already know. So in this case, we have that once again, our maximum shear stress for a circular shaft, recall, it's our torque times our radius over J. Our torque times our radius over J. So we can then say that this is the same as our torque times our radius over J for a circular shaft. Our polar moment of inertia for a circular shaft was pi over 2 r to the 4, which simplifies out to 2 t pi r cubed. When I simplify all that out, 2t pi r cubed, and we said that our maximum allowable shear stress was 8,000 psi, as was given by the problem. It's going to be equal to 2 times t times pi, and we said that our radius was 0.55689 inches cubed. Once again, this is a pretty straightforward algebraic problem to solve, and we get that our allowable torque is going to be 2170.3 inch-pounds. 2170.3 inch-pounds. Our other criteria was that our shaft can only deflect through an angle, can only have an angle of twist of 3 degrees. And remember and recall that for a circular shaft, our angle of twist was going to be given as TL over JG, which is going to be equal to T times 4 times 12 to get it in all into inches. J is still going to be pi over 2 r to the 4, which we know what r is. R is, in fact, 0.55689 to the 4. And then we have G, and once again, the modulus of rigidity for 6061 aluminum was 3.7 times 10 to the 6 psi. Okay, so we know everything on this right side of the equation but T. We have to then equate it to, once again, our 3 degrees. So we have our 3 degrees times pi over 180 in order to convert it to radians. It's going to be equal to our T. We have a 4 times 12. I'm going to bring this pi over 2. I'm going to bring the 2 up top. And we have a pi times 0.55689 to the 4 times 3.7 times 10 to the 6. So now we know everything in this equation but our maximum allowable torque. So I just solved the algebra problem. I get my maximum allowable torque was 609 609.76 inch-pounds. So once again, just like with the triangular shaft, we reached our maximum allowable torque. We reached our angle of deflection, our angle of twist, well before we met our maximum allowable shear stress. So our maximum allowable torque is going to be defined by that 3 degrees of twist. It's not going to be defined by the 8,000 psi of shear stress. So in this case, we have an allowable torque of about 610 inch-pounds. 610 inch-pounds, we can compare that to our previous triangular shaft of 444. So we got quite a bit of improvement in the circular shaft as opposed to the triangular shaft. So the big takeaway from this is that when we have non-circular cross sections, they are generally, in fact, they are always not going to be as efficient for handling the torque as a circular cross section will be. That's why we most commonly see circular shapes being used to transmit torque, because circular shapes are both more efficient in handling the shear stress and in handling the angle of twist. So they're both stiffer with respect to twist, and they have lower stress values for a given input torque, which is why we most commonly see circular shafts being used to transmit torque. Now, the only downside of that is it's a little bit harder to fasten something to a circular shaft. That's why things like square shafts and triangular shafts are used a lot, because you can build a key that slots over a triangle or a square or a hexagon a lot easier than you can build something that slots over a circle to transmit torque. But in general, circular cross-section is going to be your most efficient shape for transmitting torque in order to have both the least angle of twist in the shaft and to have the lowest shear stress for a given input torque. So we generally have our reading quiz at the beginning of class, but in today's video lecture format, I'm going to go ahead and give you the reading quiz here at the end of the video, just to kind of give the people that watch the entire video credit. So go ahead and pause the playback here and take a look at the questions. What I want you to do is I want you to then email me the answers to these reading quiz questions, and I will give you credit for those. So today we were supposed to have met for this lecture on Monday, so please do not forget that you will have an exam over chapters 1 and 2 on Wednesday. You also have chapter 2 homework that'll be due both from last week and this week. So we missed last Monday due to Labor Day, and then we're going to miss this Monday due to me being out of town. But go ahead and have your chapter 2 homework done, and please submit it to the Math Testing Center when you go sit to take your exam on Wednesday.